In this video, I'll talk about solution equilibrium and solubility. I'll talk about a specific example. The solubility of sodium chloride, that's table salt, is 36 grams per 100 grams of water at 25 degrees Celsius. What does that mean? At the room temperature, you can pour as much salt as possible into 100 grams of water. Only 36 grams will be dissolved. When 1 gram of sodium chloride or table salt is dissolved in 100 grams of water at the room temperature, we say this solution is unsaturated. What about 2 grams, 3 grams, 35 grams? They're all unsaturated. Okay, now what if I pour 37 grams of sodium chloride into 100 grams of water at the room temperature, and I store it? Eventually, 36 grams of salt will be eventually dissolved and form a saturated solution of sodium chloride. 1 gram of sodium chloride will remain in the solid state. And at this point, both the dissolution of the sodium chloride solid and recrystallization take place at the same rate. It's called dynamic equilibrium. What does that mean? That means, well, if you have 1 gram of sodium chloride solid in the solution, it's dissolving, but at the same time, the sodium plus and chlorine minus are recrystallizing. So overall, we see no net change in the amount of solid sodium chloride in the solution. Now let's make a supersaturated solution. So same 37 grams of sodium chloride and 100 grams of water. If we heat up the solution, the water can dissolve more sodium chloride, and usually the solubility increases with temperature, with exceptions. In this case, at 80 degrees Celsius, we can dissolve more than 37 grams of sodium chloride in 100 grams of water. So the solution becomes unsaturated at a higher temperature. But then we carefully cool this down to 25 degrees Celsius. And before this solution starts to crystallize, it's called a supersaturated solution. This 100 grams of water is dissolving actually more than it can. This supersaturated solution is unstable, and precipitation can happen anytime, but you can also just add a tiny bit of sodium chloride into the solution, and the crystallization will happen immediately. After that, you will have only 36 grams of sodium chloride dissolved in water. And I want you to take a look at this video. This is a supersaturated solution of sodium acetate. And this person is dipping some crystal in this solution, sodium acetate crystal. And look how fast the crystallization is going on. You're getting more and more sodium acetate crystal. All right. I saw this demo about 30 years ago. Now let's work on some practice problems. First, the solubility of potassium chloride is 34 grams per 100 grams of water at the room temperature. And how do we make unsaturated, saturated, and supersaturated potassium chloride solution? Well, it's pretty simple. Unsaturated. Well, as long as we dissolve less than 34 grams of potassium chloride in this 100 grams of water, it's unsaturated. And also, if we have only 1 gram of water, well, just dissolve less than 0.34 grams of potassium chloride. What if we have 1,000 grams of water? We just dissolve less than 340 grams of potassium chloride, right? So this is one example. We just dissolve 33 grams of potassium chloride into 100 grams of water. And then if we add 1 more gram of KCl, let's say 34, all right, and then we stir it, we wait patiently, eventually all 34 grams of KCl will be dissolved, and this solution is saturated. We can add more than 34. For example, we can add 35 grams of KCl, but eventually only 34 grams will be dissolved, and we will see again 1 gram of KCl in the solid state in the solution. So it's not really just a homogeneous solution. There's also 1 gram of solid. You can add actually much more than that. Why don't you just add 68 grams of KCl? But it doesn't matter. Only 34 grams will be dissolved. And then you will have the other 34 grams sitting at the bottom of the container in the solid phase. Okay, now what if we try to dissolve more? Well, it's possible. Usually we increase the temperature to dissolve more. So we can increase the temperature to 70 degrees, and then we can actually easily dissolve 35 grams of KCl in 100 grams of water. Again, this is because the solubility of KCl increases with the temperature increase. All right? So now if we do that at 70 degrees Celsius, this solution becomes actually an unsaturated solution. Because again, 100 grams of water can dissolve more than 35 grams at such a high temperature. Now we carefully cool this solution down back to 25 degrees Celsius. Supposedly only 34 can be dissolved, but now 35 grams of KCl is actually dissolved. It's called supersaturated. It's highly unstable, and you can add just a tiny bit of KCl in the solution to precipitate out this 1 gram of KCl. Another way is to just gently disturb the solution, or maybe just scratch the inside surface of the container. It's to create some energy for this crystallization to take place. All right, now I'm going to qualitatively tell you how to dissolve more solute usually. And I told you this, we can increase the temperature. Why does this work? Very simple. For a substance to be dissolved, the change of the enthalpy of the solution, this process, should be less than temperature times the entropy change. Again, entropy is the randomness. All right? So if the randomness of the system increases when you dissolve, for example, KCl in water, this change is positive. Temperature times delta S is positive. And if we increase temperature, we increase this product of temperature and the change of randomness. And eventually, if the temperature is high enough, this T delta S is going to be greater than delta H. Okay, and this is the condition for dissolving the substance. So if you want to dissolve more, increase the temperature. And then I'm going to contradict myself. Sometimes you could decrease the temperature. All right. So for some rare cases, really rare cases, when you dissolve a salt in water, the entropy of the system actually decreases. How is that possible? Now imagine this situation. When you dissolve an ionic compound in water, it dissociates into positive ions and negative ions. And sometimes these positive ions and negative ions have a very large charge that can attract water molecules tightly around themselves. That actually decreases the randomness of the water molecules. All right, in that case, this delta S is negative. Okay, and usually in these cases, delta H is also negative. Okay, therefore we can still dissolve some of them. Delta H is negative, delta S is negative, so we're looking at a negative number on the left hand side and a negative number on the right hand side. So you can dissolve some. All right. But in this kind of cases, if you want to dissolve more, you should reduce the temperature. You make this T lower so that this T delta S is less negative. That will ensure this T delta S is greater than delta H. All right, again, this is fairly rare. We don't see this situation very often. I think in the textbook, you see at least one example, which is cerium sulfate. Okay, that's on page 549. In figure 13.10, you can see that one salt has a higher solubility at lower temperature. So because of this. But again, this is really rare. Finally, if we're trying to dissolve a gas in water or some other solvent, we can increase the pressure of the gas. I want to be clear. You need to increase the partial pressure of the gas. So if you want to dissolve more CO2, you need a higher pressure of CO2. If you increase the pressure of nitrogen or oxygen, it does not help. All right, so a couple numerical examples. Let's say 1 liter of water can dissolve 0.034 moles of CO2 under 1 atm CO2 condition. And then if we increase the pressure of CO2 to 2 atm, the solubility of CO2 doubles. Now, 1 liter of water can dissolve 0.068 mole of CO2. Okay, when you double the pressure of CO2. Now let's talk about oxygen. So oxygen can be dissolved in water. All right, just the solubility is very small because oxygen has zero dipole moment and oxygen has very dispersion interaction as well. Okay, CO2 also has a zero dipole moment, but it's possible to induce a non-zero dipole moment in CO2. Okay. Now 1 liter of water can only dissolve 1.3 millimole of oxygen gas. So I want to emphasize this is millimole. 1 millimole is 0.001 mole, so very little amount under 1 atm oxygen. All right. So now my question is, what if I'm talking about air? What if I place a beaker of water just in air? How much oxygen can be dissolved? All right, it's only 20% of this 1.3. Therefore, only 0.26 millimole of oxygen can be dissolved in water. In air, because in air, the pressure of oxygen is only 20% of 1 atm. But this is still important. This is the reason why fish can breathe in water. There's oxygen in water. Now I'm going to show you an equation. The solubility of a gas is a constant. It's called Henry's constant. This H stands for Henry. Henry's constant times the pressure of that gas. All right, not the total pressure, just the partial pressure of that gas if you're talking about a mixture of gas. So if you're talking about air, and if you're talking about the solubility of oxygen in water, the pressure of oxygen is 0.2 atm. All right. What about the partial pressure of nitrogen? 0.78 atm roughly. Okay. So this is how you increase the solubility of a gas in water or any other solvent. You just need to look up this Henry's constant of that gas. You can find the values on the internet or in your textbook. Right? But then how can we make the dissolution faster? Well, very simple. You need to increase the contact area. So you can break the solid into small pieces if you're trying to dissolve a piece of solid, just to increase the surface area. Even better if you can make powder. That will dissolve faster than a big chunk of crystal. 2. Stir. Stir is to, again, increase the contact area between the solute and the solvent. But remember, neither one nor two can change the solubility. So you can just make the dissolution faster. All right? So this way, you can dissolve 36 grams of sodium chloride in water to form a saturated saline, but it cannot increase the solubility of sodium chloride. Also, you can increase the temperature to make the dissolution faster. However, remember this, dissolving faster is different from dissolving more. All right? So if you increase the temperature, yes, the dissolution will be faster. However, it may help you dissolve more solute or occasionally less solute. It all depends on whether the entropy of the system has a higher entropy or lower entropy after dissolution. In most cases, the entropy or randomness of the system increases after dissolution. And then increasing the temperature will help dissolve the solid faster and more. What if the entropy of the system decreases after you dissolve the solute? Well, in that case, increasing the temperature will help dissolve the solute faster. But the solubility will decrease at a higher temperature. So in this case, if you still want to dissolve more and dissolve faster, I would say, well, heat it up, dissolve faster, and then gradually cool the solution down.